This could be very bad if I forget recording. Okay, yeah. So, um, yeah, so today we're going to discuss something called adversarial examples. So what are adversarial examples? In a paper in 2013, Szigeti, I really don't know how to pronounce that, Szigeti et al. Noticed the following interesting phenomenon happens in deep learning. If you take a certain image, let's say, for example, of a bus, and you add a very small perturbation. What does it mean, a small perturbation? A perturbation that is that has a very small norm, right? For example, L2 norm, L infinity norm, something like that. Then you can create a new image that looks essentially the same, right? You cannot see any difference between this image and this image. But this perturbed image is classified as an ostrich. Ostrich is this strange bird that doesn't look like a bird, right? And so all of these images on the left that you can see, for example, here we have some type of a bird looking thing. Here we have, I don't know what this thing is. This is an angry dog, etc. So all of these images, you can create a small perturbation and you can add this perturbation to the image, and then you would get an adversarial example that would be misclassified as an ostrich. Xiaoding says that this is a Mayan pyramid. Thank you, Xiaoding. Xiaoding, sorry. By the way, is Xiaoding the first name and the second name? I feel like I might be saying, is one of them? Oh, Jack. Okay, okay, Jack. Okay, thank you, Jack. Now, in some sense, these examples are, somehow they are unnatural, maybe a bit synthetic, right? Because these are just images that, are on your computer, which are slightly perturbed and then misclassified. So what people started doing was creating real life attacks. And for example, in 2016, Sharif et al. Created adversarial glasses. What are adversarial glasses? So, except being a fashion accessory, these are glasses that if you put on, then a face recognition system would think that, it wouldn't be able to recognize you. So, for example, if this person wears these beautiful glasses, then the system would think that this person is this person. I feel like I should know who this is, but I don't know. Is this a famous person? No one knows. So here's another. She's an actress. Mila Jovovich. Jovovich. Okay. Okay. So here's another example. You have another person. Once that person wears the glasses, you see that the system recognizes the person incorrectly. Does this make sense? So, Zombie Killer, what do you mean, Zombie Killer? Oh, is that a movie or something? Oh, Fifth Element. I love Fifth Element. It's one of my favorite movies. But who was she in the Fifth Element? Leela. Who's Leela in the Fifth Element? I don't remember the names by heart. I'm sorry. The main character. There's no way this is the main character. No. She doesn't look like her. Okay, maybe I shouldn't argue this. This student seems very knowledgeable. Okay, so right. So, oh, there was maybe a question that's not related to knowledge of celebrities. Is there some connection between the perturbation in the face that the machine recognizes? Yes, there is some connection. Maybe that connection would be more clear once we look at some algorithms that are, we'll see some algorithms that create these adversarial examples, and based on them, you might be able to see what is the relation between the adversarial perturbation and the class. So it seems like this is the main character of the fifth element. Wow, I'm speechless. Now, here's another example of a real-life adversarial attack. In this case, you can see there is a system which is designed to identify pedestrians or people. And on the left, you can see there is a person that is being identified, right, as a person by a system with a bounding box. And on the right, you can see this attacker, so to speak. The attacker has this adversarial patch, which looks to me like a strange patch of colors, right? It's just something that they printed. And if a person is wearing this patch on them, then the system is unable to identify the person. Isn't this amazing? Don't you find this amazing? It's kind of cool. We're living in a futuristic world where governments are trying to spy on you using artificial intelligence, and you're taking a course at U of T where you're learning how to defend yourself by creating counter patches that will defend your anonymity. Okay, so hopefully you're motivated now to protect your anonymity. It is an invisibility cloak, exactly. I think there was something about this in the movie. What's the movie? Maybe a movie with Tom Cruise. I think there was a movie with Tom Cruise where he was trying to avoid being detected, something like that. I feel like I failed with the Minority Report. Exactly, yes. Wow, we have cinema experts here. Yeah, so you see, getting new eyes is very painful. Imagine if Tom Cruise knew that you could create an adversarial patch, right, and avoid being detected by systems. Tom Cruise should take this course. That's what I'm trying to say. So what is an adversarial example mathematically? So imagine you have an input X, right? And you're trying to create a perturbation Z so that after you, so C hat is the predicted class by the network, right? And you're trying to create a perturbation Z that would minimize some LP norm, right? This could be L2 norm, L infinity norm, or some other norms you can think about, a boot, sorry. And then C hat of X plus Z, theta means the predicted class for the perturbed image should be different than the predicted class on the original image, right? So this is an optimization problem that tries to change the mind of the classifier on the image by adding a perturbation Z. Now, is this a pleasant optimization problem? Is this something that you can solve easily? Is this something that is trivial? No, that is correct. That is correct. Now, there is another formulation of maybe I should say why not? Because C hat is basically a deep classifying network, right? And because of that, the constraint is extremely complicated. It's a complicated, non-convex, nonlinear function. Jack is asking whether the norm is on the embedding space or the input. The norm is on the perturbation, which is living in the input space. Okay. Now, there is an alternative formulation of the creation of an adversarial example where the perturbation is restricted in some LP norm sense, and the perturbation is trying to maximize the loss of the logits of the perturbed image. So here f of x plus z theta are the logits of the perturbed image, right? And we're trying to maximize the loss of the logits of the perturbed image. So let's think of the simplest loss. What is the simplest loss in my mind? The simplest loss in my mind is just the L2 loss, right? So if I have the L2 loss squared, I would get something like f of x plus z theta minus y, L2 squared. And we're trying to maximize this quantity, subject to the constraint that the perturbation is bounded. Is it clear, by the way, why do I keep writing f of something semicolon theta? Is it clear? Okay, I see some notes. Okay. Now, these are two problems. They're not equivalent. It's unclear what's the relation, right? And some people are interested in one problem. Some people are interested in the other problem. And today we'll see algorithms that would try to optimize essentially both of these problems. So here's the first algorithm. Is one problem easier to solve than the other? I would say that the second problem would looks easier to me. Because the second problem, yes, because here you have this inequality, which is kind of a strange optimization problem. I don't know many optimization problems with inequalities, but I do know many optimization problems with constraints on an LP norm. What if under this constraint, the maximum loss won't be able to change the class? In that case, you won't get an adversarial attack. But essentially, empirically, empirically, what's observed is that you need a very, very tiny perturbation that is not noticeable to the human eye, which can change the predictions, right? So if you remember in the examples that we saw here, the image after the perturbation, this is still an angry dog, right? You cannot distinguish the difference between the two. It's basically the same. So you need a very small amount of perturbation to be able to change the class. So Amir, what I'm trying to say is, Amir, yeah, you don't need a large lambda, exactly. And also, why do people find this interesting? Why is this why are we talking about these adversarial examples? Because essentially these adversarial examples indicate that the systems that people are using are unstable, as Gina said. They're brittle, they are unreliable, and they can, okay, so now I'm going to show you the first algorithm for creating an adversarial attack, which is called projected gradient descent. And this was proposed in 2017 by Alexander Madry from MIT. So the algorithm says the following. Let's look at the second formulation of the adversarial example problem, where we're constraining ourselves to an L infinity norm. Okay. Now, what they're proposing is an algorithm that initializes the perturbation to be zero, a zero vector, I mean, right? And then you take ZT, you do something that looks like a gradient step. So this is okay, let me highlight some important things. This is a gradient, but it's important to understand a gradient with respect to what? It's a gradient with respect to the input to the network. Usually when people say gradients in deep learning, they think about gradients with respect to parameters, right? This is a gradient with respect to the input. So notice how I write gradient. Here you can see the V, which is the input, and here you can see differentiation with respect to V, right? And the derivative is calculated at x plus zt, which is the current adversarial example. Now we take this gradient, and on this gradient, we apply the sine function. We multiply it by epsilon and add it to the current z. So you can interpret this as, oh, 1 second. This thing is essentially a gradient step. Essentially a gradient step. And afterwards, what they do is they take this new z after the gradient step, and they apply a projection onto the L infinity ball. So it's a gradient step together with a projection. Projection. And that gives you the new zt plus 1. So in case someone doesn't know, I'll return to this slide again in 1 minute. I just want to remind people, what does it mean projection onto L infinity ball? I'm not sure if this is trivial common knowledge or not. So the L infinity ball is defined as the set of vectors z, which have an L infinity norm less than lambda. So pictorially, in 2 dimensions, I'm sorry for the crookedness, the L infinity ball is actually not a ball, but a box. Why do we call it a ball? Just to confuse people. So this is the L infinity ball, where this is lambda, lambda, minus lambda, minus lambda. Does everyone know LP balls, L infinity ball? Common knowledge, not common knowledge. Okay. And then the projection onto the L infinity ball says the following. Imagine I give you a vector, which is, let's say, this vector, which is in this case denoted by z. So this is z. And you're trying to find the closest point, u, in terms of the L2 norm to z, which is within the lambda L infinity ball. So all you have to do is essentially do this type of a projection and return this point, right? And so mathematically, this is equivalent to saying, if your z is greater than lambda, then you plug lambda. And if your z is between minus lambda and lambda, you return the zi. And if it's less than, if your z is, I think the sign here is incorrect. I think this should be like that, right? Oh, no, it's, never mind, it's correct. It would make more sense to write minus zi less than minus lambda. I don't know why I wrote it this way. But if my, oh, sorry, it should be zi less than minus lambda. That would be the correct thing here. So I'm sorry if this is confusing. So if zi is less than minus lambda, you just return minus lambda. Does this make sense? So you apply the projection coordinate-wise. Any questions about the projection, or is this easy to see? If it's not a ball, is there intuition why it's called a ball? Because if you replace this with a L2 norm, this would be a ball. So I think it's like a generalized type of ball, if that makes sense. So with this in mind, we understand hopefully this algorithm. Now, I feel like I need to say something here, so I don't know how many people here know optimization or how many people here don't know optimization, but when I first looked at this, I was extremely confused by the following issue. The words projected gradient descent mean a very particular algorithm in optimization. And as far as I can tell, this is not a projected gradient descent algorithm. I'm actually not sure why they call it a projected gradient descent algorithm. I mean, it is a projected gradient descent algorithm in the sense that you have a gradient and you do a projection. But usually when you look at projected gradient descent algorithms in the, in optimization courses or in the literature, it's something a bit different than what you see here. But I don't want to go too much into that because I don't want to assume that people here know what projected gradient descent algorithm looks like in more classical settings. That's exactly the issue. Why do they take the sign? So it seems like Tristan is trying to, it seems like Tristan does know optimization algorithms. He seems to be aware that a projected gradient descent algorithm should not have a sign applied to the gradient. I've no, yeah, so I've, okay, my answer to you, Tristan, is that usually you see sign applied on gradients if the gradient is being done on some L infinity norm. But in this case, I don't see a reason why they apply a sign. So I would suggest that if you see, I'm being very careful about, do you see this? This is a very important part of the presentation. Do you see those? That's why I added those small things just to indicate that it's a projection, projected descent algorithm. So a more classical example of a projected descent algorithm would say, ZT plus 1 is equal to a projection of ZT plus plus alpha gradient, right? Of some function. That would be a more classical example of a projected descent algorithm. Okay, so I feel like I'm wasting too much time on this. So hopefully the algorithm makes sense. Now, prior to 2017, there was another algorithm that people proposed in 2014. I agree with the statement, Amireza, but I also don't agree because I think that you can, if you solve this optimization algorithm without using a sign, overall the Z would be bounded because of this projection, right? Yeah, so I don't want to confuse you guys. You should think of this as an algorithm that was proposed 2017 Madri. And if you get confused about why is it called projected gradient descent, forget about your education in optimization. Okay. So the next thing that we're going to discuss is something called a fast gradient sign method, FGSM. So this is probably the most well-known adversarial attack that was proposed by Goodfellow and others in 2014. And what the algorithm does is very simple. It says, take this algorithm, which we saw in the previous slides, and just take one step of that algorithm, okay? So just do one step. So you calculate the gradient of the loss with respect to the input of the network, and you just apply a sign, and you multiply it by epsilon. Do you see how this is one step of the algorithm that we saw in the previous slides? It's just one step of this, right? And by the way, I should mention that when calculating the derivative of the loss with respect to the input, let's do a simple example just for intuition. So imagine we had a multi-layer perceptron where y hat is equal to something like W3, D2, W2, D1, W1, X. So hopefully this doesn't look too strange to you, right? This is an example of a network where these are diagonal matrices due to the ReLUs, right? And these are the fully connected weight matrices, and there are no biases, just, you know, for simplicity. Can anyone tell me what would be, in this case, the derivative of the loss with respect to X? Or, yeah, so I should also define the loss. So the loss is equal to y hat minus y half squared. So using chain rule, the derivative of the loss with respect to y hat, right, multiplied by derivative of y hat with respect to X. So what do you get? You get something like y hat minus y. I guess I should switch the order. That would make it more proper. Something like that, right? That's the derivative of the loss with respect to y hat. And then the derivative of y hat with respect to X is what? Is W3 transpose D2, W2 transpose D1, W1 transpose. To me, this is a very intuitive expression to think about, because you're essentially taking a perturbation at the output and you're multiplying it by the transposes of all the operations. Is this intuitive to anyone else, or is this just intuitive to me? Is this adding to your understanding or subtracting from it? Is, I guess, what I'm wondering. It is backward, exactly. And it is like applying the network on some difference. Yes, but you're applying, it's like the transpose, right? It's the transpose operator. Okay, so the reason I like this, by the way, this type of perspectives is that, you know, the network is essentially, if you look locally, the network is a linear operator, right? Because it's just the amalgamation of all the weights and the masks. And so if it's a linear operator, you can just apply the transpose. And this is the transpose operator. So that's why I like this. So in any case, this is the fast gradient sign method. Why is it called fast? Because it is fast, right? You just need to apply one backward, you know, the complexity is equivalent to a forward pass or a backward pass. You don't have to iterate many times something. Okay, and the third algorithm we're going to discuss is called deep fool. Deep fool by Musavi Desfouli. That's kind of funny. Fouli. And Fauzi and Frossard from 2006. I never noticed this fully. What a coincidence. So this algorithm is trying to tackle this problem that we've seen previously, right? It's the first formulation of an adversarial example. And notice we're trying to minimize here the L2 norm of the perturbation, such that after adding this perturbation, the predicted class would be different than the currently predicted class. Now, here is a visualization of how deep fool works for a binary linear classification with no bias. What does that mean? It means you take your input X, you calculate an inner product with a classifier W, and that gives you a scalar, right? And there is no bias or anything, just inner product between X and W. And then if it's positive, then you classify it as being class, you know, the positive class. If it's negative, it's the negative class, right? So it's a very, very, very simple example. And in this specific example, we'll try to understand how does deep fool work. because it's very simple. So if I ask you, if I tell you, here is an example X, right? Do you see X? It's a point. And I ask you, please create an adversarial example that would minimize the L2 norm of the perturbation from the original input. So what would you do? What would your answer be? I guess the answer is presented in a slide, but yes, you want to project onto the blue region, right? So you take your point and you project it here. It's calculating a distance to a convex region. That is correct. Yes, that is correct, Jack. So mathematically, okay, so first of all, notice that we have here a decision rule, right? This decision rule satisfies the equation W inner product with X is equal to 0, right? Now, if you go to the left of the decision rule, then you get Wx greater than 0. If you go to the right, you get Wx less than 0. So what is dictating the sign? The fact that W is pointing this way, right? Because it's pointing that way, then everything that goes to this direction is going to be the positive class. Now, our goal is essentially to calculate the vector that would send X to here, right? That's our goal. So how do we do it? Very simple. You take, first of all, your vector W, and you create a unit vector. So unit vector is something like this, right? So it's W divided by the L2 norm of W. So it's this thing, right? Or I guess I should highlight this thing. So it's W divided by the, I cannot see this for some reason. Color is not good. Oops, sorry. Yeah, so this is the unit vector. Now, what we do is we take X, which is this vector right here, and we calculate a projection onto the unit vector. What does this projection give us? It gives us this blue vector, right? So this is what's happening here. You take X and you project it onto the unit vector, and you get the blue vector. And then because, you know, if you're doing an inner product of X with a unit vector, it gives you a scalar, and you need to multiply the scalar by a direction, which is the unit vector, and add a minus because you want to go in the opposite direction. Does this make sense? Any questions? Oh, I'll show what happens in a more general direction in a couple of slides. Now, notice that in our case, f of x theta is equal to W inner product with X, right? So here we have, let's highlight this. Here we have X inner product with W, which can be written concisely as f of x theta. And you can combine these L2 norms at the denominator to an L2 norm squared, and you can just copy the W here, right? Now, notice, oh, by the way, I should mention, why do I write this in this? What's the relation between theta and W in this case? Is that clear to everyone? What is theta and what is W? Just to verify we understand each other. What is the relation between theta and W in this specific case? They are the same, exactly. Yes, thank you. They are the same because theta is all the parameters of the network, right? And in this specific case, the network is just a linear predictor. Okay, so now what I'm going to do is I'm going to move to a slightly more complicated example where instead of talking about a linear function, we're going to have an affine function, okay? So notice how there was a bias added, a bias, which is just a scalar. Now, in this specific case, what do we do? So in this specific case, again, we're given a certain example X, and we're trying to perturb it to create an adversarial example, right? Now, if you think about it, what is the difference between this case and the previous case? So notice that we still have this Wx equal to 0 separating hyperplane, which is just line here, right? This is the plane of Wx equal to 0. And in our case, there's another plane which is interesting, which is Wx equal to minus b, which is, maybe I'll use a different color. It's just purple. It's this line, right? This line is Wx equal to minus b. Now, your classifier is going to classify things as being positive if Wx plus b is positive and negative Wx plus b is negative, right? So the separating hyperplane in this case is the purple line. Now, what do we want to do to create an adversarial example? We want to create a vector that would project x all the way to the purple hyperplane, right? So we want to calculate this dashed vector. So based on the previous slide, we already know that this, use this color, this thing is equal to this thing based on the same arguments as the previous slide. So the only thing that we need to do is we need to understand what is the width, or what is this vector basically, right? So we know that the direction of this vector has to be equal to w over the L2 norm of w, just the unit vector, because, is it clear why or not clear? Okay, so maybe I should explain. So if you're trying to create a perturbation from x all the way to the, let's say, to the blue line, then based on the previous slide, you know the direction in which you're going is w over the L2 norm of w, just the unit vector. And so in this specific case, you just need to go a little bit extra in the same direction. So it's the same direction of the unit vector. That's why you have this w over the length of w. The only question is how much longer, like what is the length of this second vector, right? Makes sense or doesn't make sense? It does make sense, okay. So what is the length of this vector? So you can actually find it based on this equation. Why? Imagine I take this equation and I divide both sides by the L2 norm of w. So I divide by the L2 norm of w. So what do you get? You get w divided by the L2 norm of w, inner product with x, is equal to minus b divided by the L2 norm of w, right? And then what is x on this hyperplane? You can think of x as just being a point here, right? This is x. This is one possible x, right? And what does this equation say? It says if you take this point x, right, and you, so this is the vector x, and you project it onto this unit vector, right, then you're going to, so this is this thing, right, then you're going to get minus b divided by the L2 norm of w. This is what this equation is saying, right? So based on this, what is the distance between, this point and this point? It's just equal to minus b divided by the L2 norm of w. So that's why here you can see minus b divided by the L2 norm of w. Is this trivial or is this non-trivial? I'm trying to assess the difficulty of this. This looks like almost, I don't know, second semester type of calculation, but maybe it's trivial after I explain. Wow, thank you for the compliment. So looks trivial. Okay, no compliment there. I'm just kidding. So after you know what Z1 and Z2 are, all you have to do is just sum them, right? And if you sum them, notice that if you sum them, then you get W divided by the L2 norm of W, which is multiplied by f of x of theta, because f of x of theta is equal to the inner product of Wx plus B. Okay? Now, why am I wasting your time explaining what happens in the case of an affine function? Why am I wasting your time? So that will be clear in the next slide. Does anyone have any questions about this slide? No questions. Okay. So now imagine, let's do trivia time. Imagine I ask you, generalize this algorithm to a nonlinear function, a nonlinear deep network. How would you do that? I'm looking for an answer in the form of a single word. The word is a name of a person, I believe. Think simple. No, it's not Jacobian. Oh, I guess it is Jacobian. Yes, yes, yes. That's another possible answer. Yes. Thank you, Tristan. So basically, you know, what do people do with nonlinear models? They just linearize them and hope for the best, right? That's the approach. So imagine that you have a nonlinear function, f of x. Let's highlight it. Imagine you have a nonlinear function f, which depends on parameters theta, right? So this is your deep net. Now imagine you just calculate a Taylor series expansion of this function around the point x, right? And then you do, what is Taylor series? Taylor series says the function is equal to the point, you know, to the function at x plus the Jacobian that Tristan said, inner product with the perturbation, right? And we do approximately because it's not necessarily equal. Now, this gives us a linearization of the network. And once we have a linearization, we notice that the network, is it a linear function or is it an affine function? So it's affine, right? There is no reason why a network would be a linear function. It's an affine function. Now, if you look at the previous slide, in the previous slide, we said that the perturbation z is equal to minus f of x theta, which is just applying the network on the current point, and then multiplied by w divided by the norm of w. So in this specific case, what is w? What is w in this specific case? W is just the derivative of f with respect to x, right? It's just the linearization of the function f. So basically you could write the perturbation as z equal to minus of f of x theta multiplied by the Jacobian divided by the norm of the Jacobian, right? Does this make sense? And that's literally what's written in the next slide. So the optimal perturbation norm should be squared. Thank you. Yes, 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 that is correct. So here's what's written. You do f of x theta, right? And then you multiply by the Jacobian and divide by the norm squared, as Amir Reza says. Now, in this specific case of a deep network, the network is nonlinear, right? And so because the network is nonlinear, you can just iterate this algorithm many times. Because every time you're going to get, essentially you're trying to project, okay, so essentially it's, you know, you currently have a certain hyperplane, right? You're currently here, you're trying to project onto the hyperplane, but then after you project, the hyperplane can change because it's a nonlinear function. And so you project again and again and again. It's kind of like a fixed point fixed point function. Does this make sense? Does anyone have any questions? Seems like we're running out of time. Yeah, it might be the case that I'm missing a negative. So we're running out of time, so let's keep the questions to the end of the lecture. Now, what I've presented you is how to attack binary classification models. But if you are to defend your identity against evil governments that are trying to spy on you, you probably want to generalize this algorithm to a multi-class classification problem. Unfortunately, I will not spend time going over this too much. Just, I will say that in a multi-class classification problem, instead of having just one decision boundary, you suddenly have a bunch of decision boundaries, right? And the strategy that you use when creating an adversarial example is, does anyone want to guess? What would you do if you were tasked to preserve your identity in an evil modern world and you're facing a multi-class classification algorithm? Find the closest projection, exactly. Just find the closest projection in a greedy manner and iterate the algorithm. And that's literally what they do. Okay, so at this point, you know how to create adversarial examples. But what we actually want to do, except protect ourselves, is we want to protect our companies, right? So every one of you is probably creating a startup company. You're like, I enrolled in a deep learning course. Now that I know deep learning, I'm going to utilize this technology and make myself extra rich, right? Now, in this ambition, you should take into account the fact that people will attack your models. They will attack your companies and they'll try to exploit them. So what do you have to do? You have to harness adversarial examples to protect yourself. So you want to train models which are robust to adversarial examples. Now, what would be the easiest way to create a model that is robust to adversarial examples? Does anyone have any suggestions? What's the easiest thing one could do to protect their model against adversarial examples? Train it on adversarial examples, exactly. And that's literally what people do. So for example, this paper by Goodfellow and co-authors, they say, okay, let's train a network by minimizing the loss of the network. But instead of doing the standard thing, which is minimization over theta of some, average loss on f of x theta, comma y, right? This is, for example, MSE or cross entropy. What they say is, let's replace x with what? With FGSM of x. What is FGSM of x? FGSM of x is fast gradient sign method. So just create an adversarial example and use that to train your model, right? So this is just a reminder of how the FGSM algorithm looked like in the previous slide. So we're out of time, but let me just 2 more minutes and I'll finish. So essentially what this means is that the better algorithm, so the better your algorithm for generating adversarial examples, the better your way of defending yourself against them. So for example, the projected gradient descent algorithm is capable of creating stronger, fiercer adversarial examples, right? So you could just use them. You could use the PGD algorithm instead of the FGSM algorithm, right? PGD is projected gradient descent. So one thing that's very cool about these adversarial examples is that you can, for example, take a data set. Here they take, I don't know, this is probably CFAR. And then you can look at what type of adversarial examples are created for a standard model. So for a standard model, you see that the perturbation is something that looks like noise, meaningless, right? But if you train your model on L infinity perturbations, which are adversarial, right? So if you train a model on L infinity adversarial perturbations, suddenly your adversarial perturbations become much more meaningful. The perturbation required to fool your model is suddenly not some tiny vector in high dimensional space. It becomes a much more structured vector that seems to indicate that the network is now much less fragile. And to fool it, you actually need to create, so to speak, new content in the image. So with that, we can summarize. So hopefully what you've learned today is 3 ways to attack. So you can attack people with, I guess networks, not people. Don't attack anyone. You can attack. Okay, attack to defend is the correct strategy, right? Attack to defend. So you need to attack yourself to defend yourself. That's what you should do. But hopefully you've learned today the FGSM algorithm, which is the fast sign gradient sign method, the PGD algorithm, which is just iterating these many iterations, and the deep fool algorithm. And most importantly, hopefully you've learned how to defend yourself, or rather your companies, by training on these adversarial examples. And the biggest question is, what is causing these adversarial examples, and how do the models that are being trained on them, how are they fundamentally different? And with that, I will finish today's lecture. Thank you for coming. And let's say for questions. So Jack asked, so you wouldn't use the original training data anymore? Only the FGSMs? Yes, yes, yes. Yes. As far as I remember, yes. I guess you could use also the original training data and, you know, try to minimize a convex combination of both.
On the slide that you showed a picture of panda, why after adding noise the confidence has increased? And what is confidence? I mean,
oh, confidence is the softmax probability. So if you remember, so in the case of cross entropy loss, what you do is you do something like you take a model. So let's say you do W3, D2, W2, D1, W1X, right? This is your logits. Let's denote them by, I don't know, Y hat, right? So the way the cross entropy loss works is you calculate softmax probabilities P. So P at place C is equal to the exponent of Y hat at place C divided by the sum of the exponents of Y hat at place C prime, sum over C prime. Does this make sense? If this doesn't make sense, then in the next lecture we'll actually talk about this a bit more in detail.
and now I understand the notion of confidence, but I don't understand why adding noise makes it increase.
I guess it's because if you're adding a perturbation to the model, then you can, I mean, what does it mean? You know, let me show you an example. Imagine that you have this thing, right? This is the point X, this is W inner product X is greater than 0, and this is less than 0, right? So I'm using this image from the previous slide. Does this make sense, the image? Yeah. Okay, so imagine I tell you, you know, you have a budget of 500 iterations or some type of budget to create an adversarial example, right? Then you create an adversarial example. Now, if your budget is very large, then you're going to skip all the way here, right? You're gonna make a huge leap. So if your confidence is related to the distance to the decision boundary, then your distance is very large from the decision boundary.
Yeah.
After applying. So does this answer your question or still no?
But as I can recall, visual want the perturbation to be small, so human eye can't recognize it. Or as we have in this example, it's a white noise and it's multiplied by
no, it's not white
noise.
noise. Not white noise. Adversarial noise. It's not white noise.
Okay, but I'm asking if this network is efficient, that when we have a picture of a panda, it recognizes it or classifies it with this small confidence level. But when we add a noise with a small coefficient, then it classifies it as another animal with a high level of confidence. I mean, I can't get this.
Do you agree that in a linear model, in a model where f of x theta is equal to w inner product x, do you agree that the confidence is related to the distance to the decision boundary?
Yeah, definitely.
So when creating an adversarial example, you have a certain budget. What does a budget mean? A budget means that, let's say I budget you to have a perturbation which has an L2 norm less than lambda, right?
Okay.
If I tell you you have a small budget, you would get here. If I tell you you have a huge budget, you would get all the way here.
Okay, so in this example, the budget was not low.
Exactly. If the budget is not low, you would get a very high confidence.
Okay, I get it.
And essentially, there's a function here hiding, which is saying you could create a plot of let me plot it here. You could do something like budget, and confidence. And you could study like how does this behave. So if the budget is very high, then you're going to get. So if you want to get to high confidence, you would need a certain budget, right?
Yeah.
And if you have low, then you would have. And so there's a certain function here. The question is, how fast do you get to high confidence? And based on the panda plot, because you cannot distinguish here, it means that you can get to high incorrect confidence very rapidly, which means that it's very easy to fool the network to be very confident in an incorrect class.
Okay, so the network is very insensitive.
Very sensitive.
Very sensitive, yeah.
Yeah.
Okay, thank you.
Can I ask a question?
Yeah, of course.
Do you know what the status of this problem is right now? Like, have people solved it via adversarial training? I remember I was looking into this a few years ago, and the idea was that there was like an arms race between the attackers and defenders, and they couldn't really figure out how to solve it once and for all.
Yeah, I don't think it's solved. Last time I was looking into this, I saw a paper that by Alexander Matry as well, that was claiming that if you want to have an adversarial model, then you need to train on more examples, right? As I presented. But there is a caveat, which is that if you train on adversarial examples, your test accuracy is going to suffer. And so essentially you're sacrificing test accuracy for robustness, right? Now, the paper that I was reading said that one thing you could do is just increase the capacity of the model, just the number of parameters, right? Scale the model to be larger, and then you get better test accuracy and also robustness. But as far as I remember, the test accuracy, even after scaling the model, is still does not match the accuracy of
the original.
Yeah, the original ones. And also, even if it did, scaling a model is not something that comes without a cost, right?
Yeah. I shared a paper in the chat. It's called Adversarial Examples
Yeah.
Are Features, Not Bugs. Have you read that one?
I have read it, but I've read so many papers at this point I don't remember anything.
Right. Well, it's a interesting one. They say that basically the adversarial features, like the things it's learning, which are later being exploited by an attacker, actually help it get better classification error, and that you can train a network to be insensitive to those, but then yeah, you lose test accuracy. It's a really bizarre problem.
I wouldn't say it's bizarre, because intuitively I think it's clear why this is happening. Because if you think about it, when do you get adversarial examples? Like, what causes adversarial examples? At least from my perspective, adversarial examples, you know, let's say you have a linear model. So a linear model would be y equal to, you know, let's say wx, right? Y hat. And I ask you, under which case, if I had a small perturbation to the input, would your target change significantly?
If you have a big derivative, big W matrix?
Yeah, so how does one measure bigness in this case?
Basically the Lipschitz constant, right?
Yeah, exactly. So it's literally, and I would say it's almost, I think it's not the Lipschitz constant, but rather the condition number. Lipschitz constant measures the top eigenvalue, but I would claim that you probably care about the ratio of the top to the bottom.
Okay.
And so from this perspective, you know, when are adversarial examples occurring? So if you have a bunch of WD, 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 right, multiplied by X, then if your W's are not close to being some type, you know, an isometry, if they're not well conditioned, then you would get adversarial examples. But, you know, solving this in a manner that's very proper, and, you know, people see that, you know, I guess one way to think about it is just ill conditioning of weight matrices and trying to do some type of a regularization on the weight matrices.
Interesting. Yeah, I mean, I think it's bizarre because on the surface it looks like the recognition network is modeling the human visual system because it does so well, but then it appears to be doing something else.
Yeah, that's correct. Yeah,
it's neat. Cool, thanks.
Thank you.